Today you are going to learn elementary properties, subspaces, and an important theorem. So elementary properties. These five properties are called elementary properties. Let V over F is a vector space. Then alpha dot zero vector equals to 0 dot alpha equals to 0 vector minus A into alpha equals to A into minus alpha equals to minus of A dot alpha minus A into minus alpha equals to A dot alpha. A into alpha minus beta equals to A dot alpha minus A dot beta. And last one is if A dot alpha equals to 0 vector implies either A equals to 0 or alpha equals to 0 vector. Once again, I am repeating the properties. Let V over F is a vector space. Then first one, A dot 0 vector equal to 0 dot alpha equal to 0 vector. Minus A into alpha equals to A into minus alpha equals to minus of A dot alpha. And the third one is minus A into minus alpha equals to A alpha. A into alpha minus beta equals to A alpha minus A beta. And the last one is A dot alpha equals to 0 vector implies either A equals to 0 or alpha equals to 0 vector. And now you are going to learn about subspaces. Definition of subspace. Let V over F is a vector space and W is a non-empty set contained in V. Then W is said to be a subspace of V over F if W is itself a vector space over the same field S with respect to the same operations on V. Once again, I am repeating, let V over F is a vector space and W is a non-empty set contained in V. Then W is said to be a subspace of V over F if W is itself a vector space over the same field S with respect to the same operations on V. And in a vector space V over F, there are two types of, or there are two subspaces which are of the form W equals to 0 vector and W equals to V. These two subspaces are called improper subspaces or are trivial subspaces. And any subspace of V over F other than these two subspaces is called proper subspaces or are non-trivial subspaces. So today you are going to learn an important theorem which is a necessary and sufficient condition to be a subspace of V over F. Statement. The necessary and sufficient condition for a non-empty subset W is a vector space V over F to be a subspace of V over F is that for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. Another statement, let V over F is a subspace, V over F is a vector space and W is a non-empty set contained in V. Then W is a subspace of V over F if and only if for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So you are going to construct a proof. So from hypothesis, what is given? V over F is a vector space and W is a non-empty set contained in V. Now we shall prove that W is a subspace of V over F if and only if for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. In first case, suppose that W is a subspace of V over F. Then by definition of subspace, W is itself a vector space over the same field with respect to the same operations on V. Now we shall prove that A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. Since F is a field and W is a non-empty set, let us take the elements A comma B belongs to F and alpha comma beta belongs to W implies A alpha comma B beta belongs to W. Then by the definition of scalar multiplication, since W is a subspace of V over F. So therefore clearly A alpha plus B beta belongs to W. Since W is a subspace of V over S, by using closure axiom with respect to plus on W. So therefore, A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So therefore, W is a subspace of V over F implies for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. This is the first case. And second case is conversely suppose that for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. Let us take it as the equation number 1. In this case, we have to prove that W is a subspace of V over F. To prove W is a subspace of V over F, it is enough to prove that W is itself a vector space with respect to the same operations on V. Since W is a non-empty set, by the definition of non-empty set, there exists at least one element alpha belongs to W. So therefore, alpha belongs to W and 0 belongs to F. Since 0 is a zero element in field, so clearly from equation number 1, we have 0 dot alpha plus 0 dot alpha belongs to W by scalar multiplication. 0 dot alpha is nothing but 0 vector. So 0 vector plus 0 vector belongs to W implies 0 vector belongs to W. And alpha plus 0 vector equals to 0 vector plus alpha equals to alpha. For all alpha belongs to W implies 0 vector is the additive identity in W. And now alpha comma 0 vector belongs to W, and since F is the field, so therefore minus 1 comma, B belongs to F implies from equation number 1, minus 1 into alpha plus B into 0 vector belongs to W implies minus alpha plus 0 vector belongs to W implies minus alpha belongs to W. So therefore, alpha belongs to W, there exists minus alpha belongs to W, such that alpha plus of minus alpha equals to minus alpha plus alpha equal to 0 vector for all alpha belongs to W. Here, alpha is inverse of minus alpha and minus alpha is also inverse of alpha in W. Now, alpha comma beta belongs to W and 1 belongs to F implies 1 dot alpha plus 1 dot alpha belongs to W. Now, by using equation number 1, that implies clearly alpha plus beta belongs to W. Here, plus is called closed axiom or closure axiom. So therefore, W is closed with respect to plus. And now, alpha comma beta comma gamma belongs to W implies alpha comma beta comma gamma belongs to V. Since W is a non-empty set contained in V, by the definition, W is contained in V means every element of W must and should be an element of V. So therefore, V is a vector space implies alpha plus beta plus gamma equal to alpha plus of beta plus gamma and alpha plus beta equal to beta plus gamma for all alpha comma beta comma gamma belongs to W. So therefore, W comma plus is an abelian group and hence W comma plus satisfies closure axiom, associative axiom, additive identity axiom, additive inverse axiom, and commutative axiom. These 5 axioms is called an abelian group. So therefore, W comma plus is an abelian group. Here, plus is an internal composition. And now, 0 vector belongs to W and A comma B belongs to F implies A dot alpha plus B dot 0 vector belongs to W by using property number 1, that is A dot alpha plus 0 vector belongs to W implies A dot alpha belongs to W. So A comma B belongs to F and alpha belongs to W implies A dot alpha belongs to W. So here dot is a scalar multiplication on W over F. Once again, I am repeating A belongs to F and alpha belongs to W implies A dot alpha belongs to W. Here dot is called a scalar multiplication on W over F. Since W is a non-empty set contained in V and V over F is a vector space, then every element of W must and should be an element of V. So therefore, the remaining 4 axioms is also satisfies. So therefore, W is itself a vector space. So therefore, W is itself a vector space implies W is a subspace of V over F. So therefore, A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. Then W is a subspace of V over F. So therefore, by using these two necessary and sufficient conditions, W is a subspace of V over F if and only if for A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So this is the most important question. So practice more, practice well.